Okay, welcome back here. This is chapter 7. We'll call this part 2 of the recording here. So earlier in this chapter here, in part 1, we talked about chemical reactions, equations, balancing equations, and ways to classify them. And the rest of the chapter here, we're going to talk about some calculations and then some calculations using chemical equations to help us figure out things like how much product we may produce, how much reactants we need to start with in an actual chemical reaction that we do. But first off, we're going to talk about molar mass and Avogadros number. And the first thing we're going to talk about is the mole, not the furry guy, but the mole is basically a word that we use to describe something. So in life, right, we have a lot of words that we use to describe a certain amount of something. If we say we have a pair of something, that means we have 2. If we say we have a dozen of something, that means we have 12 of it. Not used a lot anymore, but a gross is 144. You used to say that with pencils. You have a gross of pencils and stuff like that. And in chemistry, we use basically the mole. And by the way, first off, the abbreviation for mole is MOL. They had to cut something off, so they cut the E off. That again is the abbreviation for a mole. It is not molecules, which sometimes people misunderstand and think it is. But a mole is basically the amount of substances that are contained in as many elementary entities as an atom, a molecule, or a particle as there are in exactly 12 grams of the carbon-12 isotope. You may remember the carbon-12 isotope as the isotope that was chosen to basically determine the atomic masses that we see on the periodic table. So if you remember those atomic masses, some number on the bottom there, basically came from using the carbon-12 isotope. Now, what that means is 1 mole of anything will have exactly 6.022 times 10 to the 23. And the units do change. So the units of this could be particles, if you're talking about sort of particles, atoms, could be molecules, could be pizzas, could be shoes, could be anything. But for us, for the most part, we will sort of use the number with these 2 units. Atoms or molecules are most common. This number here is, as we will see, what is referred to as Avogadros number. And we'll come back to that picture, I think. Avogadro's number experimentally has been determined to be that, but most people, again, do use this 6.022 times 10 to the 23. So what does that mean? It means if you have 1 mole of hydrogen, it would contain 6.022 times 10 to the 23 atoms of hydrogen. If you had 1 mole of carbon, it would contain 6.022 times 10 to the 23 atoms of carbon. You could also use it for something like water. 1 mole of water would contain 6.022 times 10 to the 23. But water is not an atom. Water is a molecule. So we change the units on it. If you had 1 mole of CH4, which is methane, also would contain 6.022 times 10 to the 23 molecules of methane. What do we use Avogadro's number for? Well, Avogadro's number is really a conversion factor to go from either moles to atoms or molecules, or if you have atoms or molecules, to go to moles. So we really use this as a conversion factor to go between those things. And for example, if we took hydrogen here, that's an equality. And much like any equality, we could turn it into really 2 conversion factors. 1 mole of hydrogen would be 6.022 times 10 to the 23 atoms, or 6.022 times 10 to the 23 atoms is 1 mole of hydrogen. And for example, if I said I had 5 moles of hydrogen, how many atoms that would be? we would do just a basic conversion. We would start with the 5 moles of hydrogen. We want to get rid of moles. So just like a normal dimensional analysis, opposite's going to do that. So we would want to use the conversion factor on the right there to allow the moles of hydrogen to cancel out. And we will end up with, or find a calculator around here, so it's 0.022. We want to make sure we use our exponent button like we've talked about. And it looks like we end up with, we'll call it 3.0 times 10 to the 24 atoms of hydrogen. So we use Avogadro's number to do that conversion. It's really important. Sometimes people learn Avogadro's number and they feel like they need to use it in every single calculation, but you should definitely only use it if it mentions anything about atoms, molecules, particles, or you need to find something that's in atoms, molecules, or particles. If none of that's mentioned, you really shouldn't use Avogadro's number. Now, the term mole and mole is used to represent Avogadro's number. And again, just like if you had a dozen oranges, would be 12 oranges. If you had 1 mole of hydrogen, again, you would have 6.022 times 10 to the 23 atoms of hydrogen. Another more useful sort of value that we use is what is known as molar mass. So molar mass means basically a mass per mole. And molar mass has units of grams per mole, or the units of molar mass. And really, we use molar mass to go from grams to moles as a conversion, or backwards, moles back to grams. Molar mass is really like the conversion factor that we use. Where do we get the molar mass from? So oddly enough, we get the molar mass from the periodic table. So earlier we used this number on the bottom as the atomic mass, which basically is 1.008 AMU per atom. But it is numerically equal to the molar mass. And we could say that there would be 1.008 grams of hydrogen in every mole of hydrogen. And the molar mass of hydrogen would be 1.008 grams per mole. The number always stays with the grams part, and it's always 1 mole that's there when we do the molar mass. So when we do pull those numbers off the periodic table, we typically go 4 significant figures is typically how many numbers we pull off of there. We could look at sodium, which is 2299. That basically would mean that there are 22.99 grams of sodium in a mole. Or the molar mass of sodium would be 2299 grams per mole. We could say the same thing for copper. There is 63.55 grams of copper per mole. Other molar mass of copper is 63.55 grams per mole. We could use the molar mass as a conversion factor. So for example, for hydrogen, we could use it as 1.008 grams per mole up on top. Or we could flip it around and do a mole up on top and 1.008 grams. So again, if I said I had 32 grams of hydrogen, how many moles is that? I would want to use a conversion factor where the grams would cancel, which would be that one. And again, this comes from the periodic table underneath the symbol. The grams of hydrogen would cancel. And again, if I find my calculator here, I end up with 32 divided by 1.008. Looks like approximately, well, with significant figures, I got 31.7, up right, the whole number I got there, 4, 6, and so forth, moles would round up, obviously, with 2 significant figures back to 32 moles of hydrogen in this particular case. And we use this as a conversion factor to go from grams to moles or moles to grams. Again, you can find it on the periodic table. So that is silver, which is 107.9 grams per mole. That is carbon, which would be 12.01 grams per mole. And that is sulfur, which would be 32.06 grams per mole. You could also do this for molecules like water. You basically just add up all the parts. So if we went to the periodic table for each hydrogen, there's 2 of them. Each one is 1.008 plus 1 oxygen times 16 grams per mole from the periodic table gives us a molar mass for water of 2 times 1.008 plus 16 gives us 1802 grams per mole, which is the molar mass of water. We then could use this as a conversion factor for water as 18.02 grams per mole. Or a mole is 18.02 grams. So if I said to myself, I had 17.5 moles of water and I want to know how many grams that should be, I would use the conversion factor on the left there. Moles on the bottom, 18.02 grams up on top. The moles cancel. Gives us 17.5 times 18.02. We end up with, again, 315.35 grams. Sig fig wise, we really would be looking at this number, exact number. So here, 3 sig figs, we would take this guy to 315 grams of water. So we can use the molar mass for individual elements. We use the molar mass as a conversion factor for molecules. We basically just add up the parts. If we did something like CH4, we would go to the periodic table and see carbon is 1201. There are 4 hydrogens, each is 1.008. So right into the picture, maybe not the best move there. And again, here, if we sort of add everything together, 4 times 1.008 plus 12.01 gets us 1604 grams per mole would be the molar mass of CH4. Again, we could also, if we needed to do a calculation with it, use it as a conversion factor like this, or like this, and do a little dimensional analysis with it. Now, the relationship between both of those things that we talked about, which is Avogadro's number, molar mass, and so forth, is, for example, in hydrogen, there would be 1.008 grams of hydrogen equals 1 mole of hydrogen, and 1 mole of hydrogen would equal 6.022 times 10 to the 23 atoms of hydrogen. Just like if we had water, 18.02 grams of water would equal 1 mole of water, and 1 mole of water would be 6.022 times 10 to the 23 molecules of water. So really, those are our sort of conversion factors that allow us to go from using Avogadro's number, moles to atoms or molecules, or using molar mass, go from grams to moles or moles to grams. So let's take a look at this one here. How many moles of helium are in 5.46 grams of helium? So first off, we don't see anything about atoms. We don't see anything about molecules or anything like that. Again, moles is not molecules. So this is really a conversion from grams to moles. And again, what allows us to do that is the molar mass that we could get from the periodic table. We would go to the periodic table, we would find our good friend helium, and we would look at the number underneath it and it would say 4.003. What that means is there are 4.003 grams per mole, which is the molar mass of helium. Again, we could use that as 2 conversion factors. And we would now just kind of approach it like a dimensional analysis problem. We would start with what was given to us, 5.46 grams of helium. Opposites cancel, so we want to get rid of grams. So we would use the conversion factor over here. That's 4.003 grams per mole. The grams would cancel. We're basically taking 5.46 times 1 divided by 4.003 gives us 1.36 moles of helium, sig figs based off of our original number. Let's take a look at the next one, which is how many grams of zinc are there in 0.256 moles of zinc. So take a second here and see what you come up with. Okay, so let's take a look here. Again, we see grams, we see moles, we see no mention of atoms, so we should not be using Avogadro's number. Here we are going the opposite conversion, moles back to grams. We want to use, again, the molar mass to do that. So if we look up there on zinc, it depends on when your periodic table was printed, but I'll go with the one I'm looking at 6538. It says underneath it. And again, what that would mean is zinc would say 6538 grams per mole, giving us 2 conversion factors we could use, 6538 grams over a mole, or a mole is 65.38 grams. Again, at this point here, we would start with the number that was given to us. We want to get rid of moles, so we do want to use a conversion factor here on the left, 6538 grams per mole. Moles will cancel. Grabbing a calculator here. Where'd you go? There it is. 0.256 times 65.38 gives us 16.7 grams of zinc. Again, the 3 sig figs based off of that number right there. So again, these are super common conversions that we use. Molar mass, again, taken from the periodic table, and again, taking 4 significant figures is typically what you pull off of the periodic table. Let's take a look at this guy here. This is our good friend gold, and we have 1 gold atom. And we want to know what is the mass in grams. The atom right here is the keyword to, I should be using Avogadro's number somewhere. So again, we know that 1 mole of gold would equal 6.022 times 10 to the 23 atoms. So in this case, we were going to go from atoms to moles to grams. Again, Avogadro's number will be our conversion to do that part of it. And then when we get to moles, we can then use the molar mass from the periodic table to go from moles to grams. So we would also want to obviously look at a periodic table here and find gold. And gold looks like roughly 197 if you look at gold. Again, rounding to 4 significant figures. It says probably 196.998 or something like that. But basically what that means is there is 197 grams per mole is the molar mass of gold. So starting here with our 1 gold atom, again, we're going to use our Avogadro's relationship to go from atoms to moles. So 1 mole of gold up on top, and our atoms there on the bottom. 6.022 times 10 to the 23 atoms. we stop the calculation right at this point, the atoms will cancel. We're left with moles, which takes us to this part. We now could continue on with the calculation. You could also get an answer if you wanted to and then continue on, but I'm just going to kind of continue on with the calculation. We're going to now use our molar mass from the periodic table as a conversion factor to go now from moles to grams. We want the moles to cancel. So moles would go on the bottom. 197 grams would go on top. Now when we cancel, we are left with grams, which does take us to essentially what we're looking for. So now if we do the calculation, we're basically taking 1 times 1 on top times 197, hit equals, divided by Avogadro's number. Make sure you use your exponent button and divide by 1. And we end up with 3.271 times 10 to the minus 22 grams of gold. And that's a super small number, which is the mass of one individual gold atom. Now, sig fig wise, if we had one atom, it'd probably be a number we would count, which kind of would be considered an exact number, which means technically you could have done as many sig figs as you like here. I just went for 4 based off of sort of the molar mass in that particular case. Now, we could also do these type of calculations, not just with individual elements, but we could definitely do them with, things like molecules and stuff like that. So for example, let's say we had 125 grams of water. We want to know how many molecules that is. So why don't you take a moment and see what you come up with, some numbers that will be helpful. Hydrogen 1.008, oxygen 16. All right, take a moment or two to see what you come up with. Okay, so let's see how you're doing. So we want to sort of analyze what we're doing here. We definitely have grams. We see the keyword here, molecules, which again should signal I need to use Avogadro's number somewhere. So somewhere along the way, I'm going to use that 1 mole of water is 6.022 times 10 to the 23 molecules of water. I also, to do that, in order to use Avogadro's number, I obviously need to get things into moles, which means I need to go from grams to moles, which is the molar mass from the periodic table that helps us do that. So first off, we might want to calculate that. So we did it a little bit earlier there with water. We did have 2 times 1.008 from the periodic table for the hydrogens, plus basically 1 times 16 for the oxygen gave us 18.02 grams per mole. So the path here is we need to go from grams to moles. That then gets us in the proper unit to use Avogadro's number to go from moles to molecules in this case. So starting with 125 grams of water, we would then use the molar mass from the periodic table. Again, we want the grams on the bottom so that they do cancel. And again, if we sort of stop the calculation right at this point, we would be in moles of water, which is close to what we want, but we then need to go from moles to molecules. So again, Avogadro's number is what we need there. So moles are on top. And again, you could absolutely get a number here and then continue the calculation. But I'm just going to continue the calculation using the molar mass. Remember, it's always 1 mole. And we do 18.02 grams of water up on top. The moles cancel. We are left with grams at this point. So if we multiply everything on the top, 125 times 1 times 18.02, it equals then divided by, I think I hit the wrong number. Hang on a sec. I did write the wrong thing there. I'm sorry. That was Avogadro's number. So my bad here. We are using Avogadro's number here on the back end. I didn't think that looked right. 6.022 times 10 to the 23 molecules. That is what we're looking for there, obviously. So that's a little bit right there. Sorry about that. Let me just kind of scratch it out. Now let's actually multiply the right thing here. 125 times Avogadro's number now on top. It equals divided by 18.02, hit equals, and we end up with 4.18 times 10 to the 24 molecules of water is present in this particular case. And that is a very big number, which you think if you have, 125 grams of water, there's a lot of individual water molecules flying around, or not really flying around, floating around perhaps. And that does sort of justify that number. Let's take a look at maybe one more here. Let's do maybe if we had 3.2 times 10 to the 8 molecules of CO2, how many grams would that be? So why don't you take a moment and do that? Carbon is 12.01. Oxygen is 16. So take a moment and see what you come up with. Okay, so let's see how you're doing on this one here. So again, always good to maybe dissect what we got going on. We got molecules. So again, that should trigger Avogadro's number. We're looking for grams. So remember, Avogadro's number takes us from molecules to moles. And then we need to go the last way there from moles to grams. And again, it's the molar mass that allows us to do that. So might as well up front calculate the molar mass here of CO2. Going to the periodic table, we see carbon is 12.01 grams per mole, plus 2 times 16 grams per mole, which is our oxygen. That's 32 and 12. That gives us 44.01 grams per mole. Again, that is our molar mass for CO2. So we will start our calculation here with the number that they gave us. So we'll take our 3.2 times 10 to the 8 molecules. This is where we're going to use Avogadro's number to take us from molecules to moles. And again, molecules would go on the bottom. So 6.022 times 10 to the 23 molecules, which is Avogadro's number per mole. And again, if you do want to get a number here, I'll do it this time. We'll go with 3.2 exponent button 8. We're going to divide it by Avogadro's number, 6.022 exponent button 23. Looks like we get 5.318. I'm not going to round at this point. I'm going to take it to a couple of digits, just so I don't get too much rounding going on here. Remember, you don't want to really round until you get to this sort of end. At this point, the units would be moles of CO2. Now I'm ready to do my last sort of leap there. We're going to go from moles to grams. That's going to be 44.01 grams per mole of CO2. And we would then multiply it by 44.01, giving us a 2 point. At this point, we're going to round 3 times 10 to the minus 13 grams of CO2, as obviously the moles would cancel in this particular case. Okay, so as I mentioned, it's really important, that calculation of grams to moles, moles to grams, especially what we're going to talk about here to sort of finish up this chapter. We're now going to kind of put together everything in this chapter. We're going to put together the equations, the balancing equations, doing these type of calculations to do what is referred to as stoichiometry. And that's really just nothing more than kind of calculations from balanced equations. And we do this to help us understand, how much product we might make in a particular reaction. We could also know if we know how much product we made, how much reactants we started with. So when we look at a balanced equation, there's a couple different ways we could look at these coefficients. We could say an example here that 2 molecules of O2 react with 1 molecule of O2 makes 2 molecules of H2O. We could also say that 2 moles of H2 react with 1 mole of O2 gives us 2 moles of H2O. And again, these numbers come pretty much what the coefficients are in the balanced equation, nothing more than that. We could also say conservation of mass, 36 grams of reactants gives us about 36 grams of products. So when we're doing stoichiometry, we pretty much will use this relationship here, which is sometimes referred to as the mole-to-mole relationship. And that relationship is really used in a process known as stoichiometry, where we, again, ask these type of questions like, hey, if I did this reaction and I started with 5 grams of one of the reactants, how many grams of product should I produce if everything went perfectly? And again, you could also go, hey, I just did this reaction and I produced, 12 grams of the product. How much of the reactants did I actually start with? So you could do these type of sort of calculations. The units in stoichiometry can be a wide variety of units, but we typically will see grams and moles as our units, but they can be liters and other types of units. We use the mole method, which is pretty much what I just showed you there in the last slide. It's that coefficients and the mole-to-mole relationship between them. When we work these sort of stoichiometry problems, there's several steps, and really we'll condense this down to kind of 4 basic steps. But if you happen to be given things in words, you want to get the right equations or formulas. You want to always make sure it's balanced. You want to convert into moles, use the mole-to-mole relationship, and then do some other type of conversions. So the basic 4 steps that we really could reduce this down to is pretty much you always 100% need to start with a balanced equation, or none of this will work. So if you are given an equation, you need to make sure it's balanced. If you're given an equation that doesn't have any numbers for the coefficients, you probably should take a moment and make sure it's balanced. If you're given, again, in words, you want to turn it into an unbalanced equation and then balance it 100%. That is the most important thing. Number 2 is whatever they give you in terms of units, you need to convert those to moles. Typically speaking, grams are a common unit, and typically speaking, going from grams to moles is a very, very common conversion, which is what we were just talking about. Again, we use the molar mass from the periodic table to do that. Once you have it, number 3 is really the stoichiometry part of it, is the mole-to-mole relationship. So you go to the balanced equation and you find the 2 things you're interested in. One thing is whatever they gave you. The other thing is what you're trying to find. And you use those coefficients to get the mole-to-mole relationship. Lastly, a lot of times you'll be in moles at this point. You need to do a conversion to some other units. So a lot of times it's moles to grams, using the molar mass on the back end of the calculation as something that we commonly do in these type of problems. So let's take a look at sort of some of this here. I'm just going to kind of explain it. So let's say we have this balanced equation here. From this one balanced equation, we could come up with a lot of mole-to-mole relationships, and they do come from the actual coefficients. We could say that for every 2 moles of CO, it reacts with 1 mole of O2. Again, that comes from the coefficients here. We could also say for every 2 moles of CO, it reacts with 2 moles of CO2. Also, again, just the numbers here from the balanced equation. We could say for every 1 mole of O2, it is equal to 2 moles of CO2. So again, 1 mole of O2, 2 moles of CO2. So here's the deal. Obviously, 2 doesn't equal 1, or 1 doesn't equal 2. These are what are referred to as being stoichiometrically equal to each other. And what that essentially means is it's kind of like a ratio. you need to throw in there like 2 moles of CO and 1 mole of O2 to get this reaction to take place. It's kind of like when you make cookies, you need to put in so much flour, so much chocolate chips, so much butter in order to get like a dozen cookies made, when you bake them. And that's basically what these are. The purpose of stoichiometry is because when we have these problems, we're usually given information about one thing in the problem. So, for example, let's say we were told, hey, we started Okay, let's take a look. So starting with our first one, balance the equation. I do see coefficients here, and we did it last time, so it is balanced. Next is convert what they gave us. So in this particular case, they gave us 81.75 grams of lithium, and we want to convert those to moles, and we do need to do that. So we would go to the periodic table. We see lithium is 6.941. That means that the molar mass of lithium, 6.941 grams per mole. That's what we would do here to do our conversion step here. 6.941 grams per mole of lithium. Grams will cancel, and we end up with 81.75 divided by 6.941. Gets us, we'll call it 11.77. I'll take it to a couple digits here, moles of lithium. Now we're still in lithium. Remember, we're ultimately looking for H2. So again, we need to do the third step here to find a relationship between the two things we're interested in. And again, we see that for every 2 moles of lithium we put in there, which comes from the coefficient, we get 1 mole of H2, also comes from the coefficient. That again gives us the same conversion factors we saw a second ago, which is 2 moles of lithium over 1 mole of H2 are 1 mole of H2, 2 moles of lithium. We're going to continue on with our calculation. We're going to take that number down. And again, just thinking about it like dimensional analysis, I need to get rid of lithium, which means I do need to use this conversion factor here. 2 moles of lithium is 1 mole of H2. Moles of lithium will cancel. That gives us, divided by 2. We'll again take it to a few digits here, 5.8889 moles of H2. We've now gone from lithium to H2. That has now done the big stoichiometry problem. But in this particular case, we're looking for grams. So we're actually not done. So we've done number 1, we've done number 2, we've done number 3. In this particular case, we now need to do number 4, which is to go from moles, in this case, to grams. A couple of things you do need to be careful of. We need the molar mass, but remember at this point, we have now gone from lithium to hydrogen. So we actually need the molar mass of hydrogen, which would be 2 times 1.008 grams per mole. And that would now get us 2 times 1.008, 2.016 grams per mole. And again, we're going to use that in step number 4 here. If I can find where my pen is. There it is, 4. We're going to take our number from above, 5.889 moles of H2, using the molar mass of hydrogen, 2.016 grams per mole of hydrogen. The moles will cancel, and we will end up with, it looks like, looks like 11.87 grams of H2. And again, if you're curious where these 4 sig figs came from, it was from the one and only number given to us in this particular problem, which was 81.75, had 4. So our answer has 4 significant figures. Again, you can see, hopefully, it is the same 4 steps: balance equation, convert to moles, mole to mole relationship, moles to some other unit. Again, sometimes you need to do all 4 of them. Sometimes you just need to do 3 of them. Sometimes you can skip a step along the way. What does this mean? Again, here, if we were to do this reaction and we threw in there 81.75 grams of lithium, everything went perfect, we should expect to get out 11.87 grams of H2. This is what is sometimes referred to as the theoretical yield. which is how much product you should produce in a reaction if everything went perfect. All right, so why don't you give this one a go and see what you come up with. We want to know what is the mass. So we want to know how many grams of CO2 would be produced in this reaction. I'll give you some numbers here that would be helpful. Carbon 12.01, oxygen 16, and perhaps you need hydrogen as well there, 1.008. So take a couple moments, see what you come up with. Again, follow those same 4 steps. Trust me when I tell you the same 4 steps as soon as you recognize the stoichiometry problem. So I see an equation, it is balanced. So that's step number 1. Step number 2 is to take whatever they gave us, which was this right here, 765 grams of C6H12O6, and we want to convert that into moles. That means that we do need to get the molar mass of this guy, and we would get the molar mass from the periodic table. So 6 times 12.01 plus 12 for the hydrogens times 1.008 plus 6 times 16. And that will get us 6 times 12.01 plus 12 times 1.008 plus 6 times 16. Looks like about 180.2 grams per mole. So again, we're just going to use that as really a conversion factor to go from grams to moles. So grams need to go on the bottom so that they cancel. And again, here we'll do a step by step, so we'll get an answer. So 765 divided by 180.2. And again, I'm not going to round too much here early on. So 4.24528 moles of C6H12O6. Next step is to do the mole to mole relationship. So looking at the equation, we were given information about this guy. We are interested in CO2. So we do see that for every 1 mole of C6H12O6 we put in there, we get 6 moles of CO2. Again, nothing more than the actual coefficients. Again, that gives us 2 conversion factors that we could use, which looks something like this, or like this. And again, carrying down the number from the previous step gets us 4.24528 moles of C6H12O6. Remember, we want to cancel that out as this is the stoichiometry part, which means we do want to use a conversion factor on the right to do that. 6 moles of CO2, which is what we want to end up with in terms of CO2 on top. This guy here on the bottom, these guys cancel. So we will take that number and times it by a 6. Looks like we end up, again, not rounding too much at this point, 25.4717 moles of CO2. So we have successfully converted from C6H12O6 into CO2. The last step is we do need to do, we now want to take those moles, in this case, to grams. So we do need the molar mass, but again, remember at this point, we're now at CO2. So we don't want to use the same number because that's not for CO2. So we again need to go back to the periodic table and figure out the molar mass for CO2, which is 12 grams per mole there for the carbon, plus a 2 times 16 for our oxygen gives us 44.01 grams per mole for CO2, carrying our number down here to the end, 25.4717 moles of CO2. Actually multiplying in this case by the molar mass, 4401 grams on top and a mole of CO2 on the bottom. They cancel. now we will get times 44.01. We get a number like this, 1121 grams of CO2. At this point, we do want to look at sig figs. Remember that this was the only number given to us. That is 3 significant figures, which means we do want to end here. So perhaps 1120 grams of CO2 would be appropriate. Again, here you can hopefully see it is the same 4 steps, just repeated. Again, if something's done for you, you just continue on to the next step, but it is basically the same 4 steps. I clearly did this one and the last one in sort of pieces or parts, if you will, like did one calculation, got a number, did the next calculation, got a number, did the next calculation, got a number. Again, try not to round too much if you do it that way. You absolutely could do it all in one calculation, basically just kind of putting that and that, oops, and then that. So you can do it all in one calculation, should give you the same answer as well. Same 4 steps. So step number 1 is balancing the equation. I see coefficients probably balanced. Step number 2 is we want to convert to moles. In this particular case, the only number they gave us was we are starting with that guy right there, 0.7752 grams of K2PtCl4. Again, if it was not given to us, we would go to the periodic table to get that number. But since it's given to us, that was nice. Well, we'll just use it. And that would be 415.1 grams on the bottom. So the grams cancel. Moles up on top of PT. Wrong thing there. Right, the right thing there. Try it again. Moles of K2. PtCl4. This again is basically step number 2. I have stopped right now. I am in moles of K2PtCl4, but I'm not interested in that. I am interested in going from this guy to this guy here. And when I look at the equation, I see for every 1 mole of the guy that I was given, I get 1 mole of this scary guy here. If I could get that in the screen, maybe squeeze it in there. And again, that obviously gives us 2 conversion factors. Here we're going to use that. I'm just going to do this all in one calculation here. So the moles of K2PtCl4 are on top. So I want to go opposite to cancel. And up on top would then go 1 mole of our product, which is what we're looking for. And if I stop right now, the moles of those guys cancel. I'm in moles of the product, which is this cisplatin here, but I don't want the moles. I actually want the grams. So I do need to do the 4th step and use the molar mass from the periodic table, which is the 300 number that was given to us, to do our last step, which is 300.1 grams per mole of PT NH3 3Cl2, looks like. And those guys cancel, and now I'm left with grams of what I'm looking for. So multiplying all the way across the top there, it looks like we got 0.7752 times 300.1 divided by 415.1. And that's it, I think, on that. We end up with a number of 0.5604 grams of our product, which was the PT-NA3-2Cl2 is produced. Again, you could have done it step by step like we did the last couple and got an answer after each of these steps, and then ended up at the end with what we were looking for there. A reminder as well that basically these are still the same 4 steps. Step number 1, balance equation. Step number 2, convert to moles. Step number 3, the mole-to-mole relationship. And step number 4, moles to grams gives us our answer. So with stoichiometry, even though it may look scary, some of the problems, some of the formulas, all you have to remember is those same 4 basic steps: balance the equation, convert to moles, mole-to-mole relationship and convert moles to grams or some other unit, and you really will sort of have the pattern of what you need to do. All right, that wraps up stoichiometry. It also wraps up this chapter for chapter 7. So thank you for listening here to the recorded lecture to keep us on pace, with our exams and holidays that we've had. And again, obviously, if you have any question on this, please feel free to ask anytime, or during discussions, a great time as well. Have a good rest of your day whenever you're listening to this, and I will see you next time.